Hello there. In this lecture, I'm going to continue looking at the multi-degree of freedom equations of motion, and then what we'll do is we'll look at the free vibration also, okay, of multi-degree of freedom systems. Okay. So now to continue off where I had left off. Last time I had started with, I ended with talking about the lumped mass formulation and how nicely it makes the problem better. So, let us just go and review that again. Okay. So, what you have is you have in the consistent mass formulation, now note that the consistent mass formulation and the lumped mass formulation. Note that these are only at the member levels, they are distinguished only at the member level and not at the structure level. Okay. These two approaches are only at the member level. Okay. So this we saw, and that all that happened was that in the consistent mass formulation you have a full matrix, because at the member level V 1, V 2, V 3, V 4, there are 4 degrees of freedom, right. Just let us revisit that a little bit. Okay. At the member level you have V 1, V 2, V 3, V 4. Okay. So, in the consistent mass matrix, the mass matrix corresponding to V 1 dot and V 2 dot and V 3 dot and V 4 dot, full matrix, and this is consistent. Lumped M since a lump mass is lumped at these two ends, V 1 and V 2, it is completely 0, and the only thing that we have is, so it is not only a diagonal matrix, but corresponding to these two, it is a 0 matrix. Okay. So the entire lumped mass, I want to keep on emphasizing this point, because it disturbs me today to see that people do not understand where the lumped mass formulation came from, and they continue using this lumped mass formulation for kind of situations where you do not, it is not valid. Let us be very, very clear. The lumped mass formulation was created for only framed structures, where floor masses are significantly larger than member masses. Okay. This is very, very clear. So, in other words, frames where floor masses are significantly larger than the member masses. For this, lumped mass formulation is okay. Now, I will show you how ridiculous the lumped mass formulation becomes if you do this. Okay, if you remember, okay, when we have this, remember this as the degree of freedom, that single degree of freedom with E I and m bar, we had done it, and we got what? We got that m star was equal to 0.228 m bar L, and k star was equal to 3 E I by L squared. Think back, look back at your thing, and this actually is 0.227. 0.227 and 3 E I by L cubed. Okay. Now, if I were to do this, and I will say that look, this mass which is over here, I'll lump half here and half here. If I do that, okay, what does my m star become? My m star becomes 0.5 m bar L. Obviously, when I do this, half the mass goes. So, you see this? You see how ridiculous this is? If you use it in this kind of a situation, this becomes completely ridiculous. However, think about it. Here, let me put this. I put a point mass at this point, and I say that this is 10 m bar L. If that is 10 m bar L, then what is my m star? If I use this, my m star becomes 10.227 m bar L, and if I use lumped mass, I get 10.5 m bar L. Not too different, huh? Now, you see, something that looked ridiculous becomes non-ridiculous when you have floor mass. Okay? And this is the floor mass, because this mass is now very small compared to the floor mass, which is what happens in typical frame buildings, right? The floor weights that you have are significantly larger than the member weights, always. I mean, which is why in gravity loads, you pretty much always consider the weight that come from the floors as part of the gravity load. I mean, you'll see that reactions. You pretty much look at the reactions. You'll see that if you add up all the floor weights, you'll see that the floor loads, and you'll see that that is almost the reaction. Very. So if you see, this one doesn't look ridiculous. So, therefore, let us be very, very clear that the lumped mass formulation is only valid for framed structures. Okay. But having said that, now, why is it useful for framed structures? We saw that. We saw that for this particular problem that we looked at, right, the specific problem that we looked at. I don't need to put it, we got this as my V1, V2, V3, okay, and for this we developed the K matrix, and then we developed the consistent M matrix and the lumped M matrix, and in the last time we saw that ultimately what happened, that if you use the consistent matrix, then you have a again, I am still not talked about loading. So, I am putting it as 0 load. Okay. If you do this, you have in this particular case 3 coupled linear ordinary differential equations to solve. And if I use the lumped mass, I showed that all you needed to do was solve which is 1 linear ODE, and you needed to solve. Then once you solved for V1, V2 and V3 you could get from minus k theta theta inverse k theta t Vt. So, in other words, we are still, it is not as if we are still, this is still a 3 degree of freedom structure. Nobody can take away from the fact that this is a 3 degree of freedom structure. It is 3 degrees of freedom. So, you still have to find out V1, V2, V3 and the time histories of V1, V2, V3 to be able to solve this problem, because once you know V1, V2, V3, you can always find out what are the internal forces, etc. This is a standard procedure. Okay, I mean, which is essentially note that if you have time history, you can find out the bending moment at any point, because then it becomes essentially a static problem. I mean, static problem, pseudostatic problem, because at any instant of time t, you can find out what V1, V2, V3 are, and you can find out what the other forces are. Okay, so that is not. So, in other words, you still have to get V1, V2, V3. The only thing that happens is that the dynamic problem, which is ODEs. Okay. So, therefore, static still 3 degrees of freedom, consistent mass, dynamic also 3 degrees of freedom, because you still have to solve 3 linear ODEs and they are coupled. Use the lumped mass formulation, then dynamic single degree of freedom. You see the advantage? Okay. And this is in essence what essentially is why people tend to use the lumped mass formulation for framed structures, because it simplifies the problem. We in the dynamic problem, we statically condense out. This is the static condensation. If you use the lumped mass formulation, all rotational degrees of freedom, okay, are statically condensed out from the equation, and the only dynamic equation, the dynamic degrees of freedom are all the translational degrees of freedom. Okay? Only the translational degrees of freedom are the dynamic degrees of freedom. So, therefore, if I have a single story building, I have only 1 degree of freedom, dynamic degree of freedom, and so therefore, even if this beam, remember, if this beam was rigid, then these V2 and V3 would be 0. See, note that if this beam is rigid, V2 and V3 are 0, and it is a true single degree of freedom structure. But if it is not a rigid beam, this beam is not rigid. If this beam is not rigid, then V2 and V3 are not 0. If V2 and V3 are not 0, then what happens? Then we can still solve the dynamic degree, a dynamic problem as a single degree of freedom problem. The only thing is that through the static condensation procedure, we statically condense these out. So, that once we have solved for the translational degree of freedom, then you use the transformation matrix to get the V2, which V2 and V3, which are the rotational degrees of freedom. So, the difference is that you still solve a dynamic degree of freedom, only a single degree of freedom, but then you have to go back and use this to get these 3, and once. So, you have to find out these 3. It is just that you have to find out the time history of all of these to be able to get any response. You need to do that. Okay. Only thing that happens here is that the fact that you only dynamically solve for this, and these two then become just a pseudostatic relationship rather than a dynamic relationship. So, that is why the lumped mass formulation is a preferred formulation to the consistent mass formulation. The advantage of the consistent mass formulation is that it it gives you a kind of a specific, whatever frequencies that you get. We will now start solving the free vibration equation, but whatever frequencies that you get, that they are upper bounds. If you solve the free vibration equation using the Lampmass formulation, you cannot say that the frequencies that you get from the Lampmass formulation are upper bounds. They are close to them. If you use the Lampmass formulation properly and use it properly, then it will give close. The consistent mass formulation, the Lampmass formulation give reasonably close answers. Okay? But the fact remains that you are essentially saying that it's an approximation. Okay? And it's an approximation. You don't know whether the frequency is higher or lower, whereas the consistent mass formulation, that the frequency that you get from the consistent formulation is going to be higher than the true frequency. For the Lampmass, you can't. But it doesn't matter. Who cares whether it's an upper bound or a lower bound? It's only mathematicians who are interested in that. As engineers, we couldn't care whether it's an upper bound or a lower bound, as long as it's close enough to the true value. Where it is, who cares? Okay? So, that in a sense turns out. So, therefore, reviewing whatever I have done, I have formulated the equation of motion for a rigid bar kind of a situation, okay, and I have also solved it for a flexible, where I have flexible bars, and it's an assemblage. So, therefore, I have looked at equations of motion. I started off by looking at multi-degree of freedom equation of motion using rigid bar assemblages, which have more than 1 degree of freedom, okay, to establish certain basic premises, and then I looked at assemblages of flexible bars. So, in a way, I am following the same principle that I used in the generalized single degree of freedom, excepting that I am using it in the multi. With rigid bars and springs, etc., it becomes slightly easier to establish certain rules, and then we looked at it does not have to be, it can be flexible. The only thing that I must add is that even if it is made up of uniform members, okay, the K matrix and the M matrices are approximations of the true thing, purely because if you look at any structure, okay, if you look at this structure, I say that look, by defining this as a member, this as a member, and this as a member, I made it into a finite degrees of freedom problem. Okay? But actually, if you look at this, this is a continuous member. Okay? So, it actually has infinite degrees of freedom. Okay? What did we do? We actually kind of created members. From that, we got finite degrees of freedom, and once you got the finite degrees of freedom, we find out K and M. And please note that these are always approximate, except for rigid bar assemblages. Except for rigid bar assemblages, and rigid bar assemblages, the K and M are actually, you can get them exactly. But if you have flexible, because of the fact that we used xi I x as the cubic Hermitian polynomials, these do not represent the dynamic behavior at all. And so, therefore, K and M are always approximations. And which is why, since K and M are anyway approximations, the lumped mass formulation has this beauty about it. Okay. So, now let us look at finally loading. How do I get loading? Well, I have already done it for rigid bars. Let us look at flexible bars. In flexible bars, let us take any arbitrary loading on the system. Okay. So, this is given as p bar x of t. So, if we say p bar x of t, okay, and these are my what do I have? Well, I have this situation that again I take slices. So, p bar x t dx is the load, okay, and so this is the load. And so, if I want to find out p I, what is p I? P I is the equivalent load corresponding to V I, the degree of freedom V I. So, if this is the load per unit length, then if I use the formulation, you will see that P I is nothing but integrated over the whole length p bar x of t into xi I x dx. Again, this is known as the consistent load formulation. This is a consistent load formulation. I can also use another approach, which is the static resultant approach. Which is static resultant? Well, I consider this as a simply supported beam. If I find out a simply supported beam, I only get reactions, I do not get any moments, and so if I use static resultant, I only get corresponding to P I corresponding to V 3 V 4. P I corresponding is equal to 0 corresponding to V 1 and V 2. This is what happens. Okay. So, therefore, again where does this thing happen? So, therefore, now once you develop this at the member level, you can put them together corresponding to the this thing by using principle of virtual displacement. I am not going to go there. These are things that we have already covered many times in earlier courses, and I do not want to go there. Please use principle of virtual displacement to get the load. So, now the question becomes that I finally have this problem m v double dot plus k v is equal to p. Now, if I use the consistent mass formulation, then it is obvious that I have to use the consistent load formulation. In other words, xi i's are used consistently for k, for mass and for load. Okay. However, if you use the lumped mass, see, lumped mass you get to do what? Use static condensation. If you do static condensation, then you should use the static resultants approach, because what happens? In static resultant approach, we saw that forces in member forces corresponding to rotational degrees of freedom are 0. Okay. So, if you use this, then you can do static condensation, because even at the global level, the P i's corresponding to the rotational degrees of freedom are 0. Okay? So, that in essence is the procedure to develop the property matrices corresponding to any set of degrees of freedom. And again I want to establish that the equations of motion are what? Are corresponding to a set of degrees of freedom. So, if you use different degrees of freedom, your mass, stiffness and load, mass and stiffness matrices and load vectors are going to be different. I have showed you that in the 2 lectures ago. So, I do not want to continue that. I just want to establish that if you are using the consistent mass formulation, combining consistent mass formulation with static resultants or using lumped mass formulation with consistent load formulation makes no sense whatsoever. So, when you use consistent mass formulation, use the consistent load formulation, okay, and if you use the lumped mass formulation, use the static resultant formulation for the load, and then you can get. So, therefore, ultimately the whole idea of the lumped mass is that dynamic degrees of freedom become different from static degrees of freedom. This is one takeaway. Why? Because since the rotational degrees of freedom do not have any inertia associated with them and neither do they have any loads associated with them, then the rotational degrees of freedom are related to the translation degrees of freedom through a static equation, and therefore, we can condense out the rotational degrees of freedom and get the dynamic degrees of freedom in a framed structure are only the translational degrees of freedom, and therefore, the size of the problem becomes that much smaller. For example, in a 1-bay 1-story frame, what do you have? You had 3 degrees of freedom being 3 static degrees of freedom being taken into 1 dynamic degree of freedom. Okay. So, that becomes the essential issue that we roam around. So, now I am done with generating degrees of freedom for equations of motion for multiple degrees of freedom, and of course, I have concentrated on rigid body assemblages, and flexible body assemblages I have only looked at framed buildings, framed structures. Okay. And in fact, buildings purely because lumped mass formulation, consistent mass formulation give exactly similar results when you have buildings where flow masses are significantly large. Anyway, so much for the equations of motion. Let us now move on, because ultimately equations of motion have to be solved. Okay. So, to solve the procedure, the next thing that I look at is free vibration. Okay. And in free vibration, the equations are because there is no load. Free vibration means it is freely allowed to vibrate, where you are given. Now, this is the issue, that this is a vector. So, you have to be given all displacements at time t equal to 0 and corresponding velocities are given. So, here the difference becomes that there it was just given initial conditions. This is you have to be initial condition means you have to be given displacement corresponding to each degree of freedom and velocity corresponding to each degree of freedom, initial displacement, initial velocities, those are the initial condition. Now, mathematics says that look, this kind of a situation V is equal to actually V omega n sine. So, I am not going to put it as omega n, I am going to put it as omega. So, therefore, you see it still remains the same. although again classical sense I am putting sin omega t, it actually is e to the power of s t, but then we know that s blah 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 and all, and so I am just going with sin omega t. All of this is irrelevant. I am not going to go through the same procedure that I have gone through. The only thing that says is that for this to be solved, V has to be of this form, where phi is the amplitudes of displacements at every point, and this is given in this form. So, if I substitute this into the equation, I get the following. I get V is equal to the displacement. So, V double dot is equal to phi minus phi omega squared sin omega t. So, therefore, what this becomes then is the following: m into V is nothing but m multiplied by minus phi omega squared sin omega t. Okay. Now, note this is n by n and this is n by 1, because this is n by 1, this is n by 1. So, this is n by 1. Okay. So, this is this minus and then plus k into phi sin omega t is equal to 0. Now, note that since sin omega t is not equal to 0, this equation is only satisfied when I have k minus omega squared m into phi is equal to 0. This has to be satisfied. Now, if you look at this, does not look similar to what I had done there. It was a single k, it was minus omega squared m, and so omega is equal to root k upon m. In the single degree of freedom, we could do that, but note that these are n by 1, and this is also n by 1. These are n by n matrices, and so therefore, this problem is not a problem which is tractable. So, this problem essentially becomes, I am going to rewrite this problem, and this problem is k you see, this is not a problem that we are unfamiliar with. If you look at your matrix algebra, sorry. If you look at your matrix algebra, remember that any matrix, a square matrix, it always has to be a square matrix. As you were always asked to find out the eigenvalues and eigenvectors of this matrix A. And how did I find out the eigenvalues and eigenvectors? Okay. These were done by solving A minus lambda I, where I is the identity matrix, into phi is equal to 0, where this is the eigenvalue and this is the eigenvector of the matrix A. And this problem was known as an eigenvalue problem. Okay. So, if you look at this, this kind of a situation, k minus omega squared m, it is pretty much similar. All I have to do is, if I pre-multiply both of them by m inverse, you will see that this will become then, the problem will become m inverse k, and m inverse into m omega squared I into phi is equal to 0. So, you see the A matrix is this matrix, and omega squared is like an eigenvalue. Okay. So, this problem is also an eigenvalue problem. Okay. So, this is also an eigenvalue problem. Now, how do we solve this eigenvalue problem? Well, let us look at it. I am going to just put down the procedure. Solution of eigenvalue. Problem. So, what do we have? We have the eigenvalue problem is this problem. This is the eigenvalue problem. Now, for this to be valid, since phi is non-zero, it implies that k minus omega squared m, the determinant, this is the determinant, is equal to 0. Determinant is a scalar, so that is equal to 0. Now, there are certain aspects associated with this, and this comes from linear algebra, okay, matrix algebra, and that is that we know that these are symmetric matrices. We know this, we have already shown this. We will also show you that indeed these are what are known as positive definite matrices. What does positive definite mean? Positive definite is the following. Let us take any vector v, displacement vector v, right? Displacement vector b, it is a displacement vector. Okay? Now, what is k into v? K into v is the elastic force vector, right? By definition is the elastic force vector. Okay. So, now let us see. So, therefore, let us look at this. This is n by 1. This is a n by n. This is a n by 1, and this is obviously an n by 1. This is the displacement, this is the elastic force vector corresponding to those displacements. Okay. Now, I want to find out the work done by F s undergoing V. Now, work done is a scalar. How do I find this? W is equal to V transpose F s. Note that what we are doing here, work done is it is actually, this is going to be equal to summation I going from 1 to n F s I into V I. That is what it is, right? So, if you look at this in a matrix format, it can be written like this. If you look at this, this transpose is basically the vector 1 n by 1 becomes 1 by n. So, the column vector of displacements become the row vector of displacements, and then if you multiply, you will see that V I is being multiplied by F s I, which is really this. So, the work done is this, which is also equal to this. So, if I do this, this is equal to, substituting this, it becomes this. So, work is this. Okay? And we know that work done is always greater than 0. I mean, if work done was less than 0, it would be a beautiful situation, right? By making forces undergo displacements, we would actually get work which we could use, energy which we could use somewhere else. Okay. So, therefore, this, if you look at it, this is like an energy term, and energy is always positive. Okay. So, this implies, if this is true, if any arbitrary displacement into k in this format is greater than 0, then k is positive definite. So, obviously, k is positive definite. K is positive definite. Similarly, we can show that m is positive definite. How do we do it? Well, in exactly the same way, f I is equal to m into v, which is equal to omega squared m into v, and from there you can solve exactly the same way, work done by the inertial forces, blah blah blah, and you get exactly that this is positive definite. So, we see that these are symmetric positive definite matrices. Well, if they are positive definite matrices, what is the beauty of it? Well, so K, M are symmetric positive definite matrices. Now, the linear algebra says that if this is true and you find out the determinant, and that has to be 0. You see, determinant, what will happen is, this is a n by n, this is a n by n. Okay. What they say is that all omega squareds will be greater than 0, and you will have n distinct. So, if k and m are symmetric positive definite, all omega squared values, the omega n squared, there are n distinct omega n squared values for which the determinant is equal to 0, okay, and all of them are greater than 0. What is the beauty of this? Well, this means that you have omega n real. That is what it means. And of course, omega n by definition is the frequency of natural vibration, and therefore, it is not only real, it has to be positive. Okay. So, there are n distinct. So, that means what we get finally is the following, and that is that you have, by solving this eigenvalue problem, this eigenvalue problem is solvable for n omega n values, okay, and every omega n, okay, for a specific value of omega n, you find out phi n. So, every omega n has its own corresponding, and there are n such omega n and phi n. Now, this omega n squared are known as eigenvalues, and these are known as eigenvectors. Note that it is always true that the eigenvector, because the determinant is equal to 0, okay, that means it becomes one less rank. So, phi n is not a vector, is not a displacement vector, it is a mode shape vector. Why? Because if this determinant is 0, this problem becomes of rank n minus 1. Okay. The rank of the matrix is n minus 1. If the rank of the matrix is n minus 1, you can only get phi n cannot be obtained directly. It will always be obtained in such a way that you can get n minus 1 values in term of another value. Okay. So, this is like a mode shape vector. Okay. And these are my natural frequencies of the structure. So, ultimately what do I have? If I have an n degree of freedom structure where I define V as my n displacement quantities, okay, then corresponding to them we get the property matrices K and M. So, note that these correspond to the degrees of freedom. These are size n by n, and we have already developed how to get M and K through this thing. Then by solving determinant K minus omega squared M, okay, you get omega n equal to 1, 2, 3, 4 to n, you get n, and corresponding to every omega n you have a phi n, and these are the frequency, natural frequency and mode shapes of the structure. Now, note this is very, very important. These are invariant of degrees of freedom. Why? Because these are dynamic characteristics of the structure. So, now the question becomes this, that M and K are dependent on the degrees of freedom that I define. Okay? But the omega n and phi n that I get, the phi n, okay, would correspond to the degrees of freedom. Okay, but omega n does not degree. So, the phi n gives a shape, but the mode shape, once it gives that shape is an invariant. Okay. So, the frequency and mode shapes are invariant of how the degrees of freedom are defined. Okay. So, therefore, the question then becomes this, that if I have n degrees of freedom, if I have n degrees of freedom structure, I get n frequencies, natural frequencies, natural frequencies and corresponding mode shapes. Now, the question, so if I have an n degree of freedom structure, I have n natural frequencies and corresponding mode shapes. Okay. So, and we have to solve the eigenvalue problem. I'm going to start solving the eigenvalue problem, how to solve, we will solve examples in the next lecture. But now, for example, it becomes very interesting that if I have n degrees of freedom, and this is dynamic degrees of freedom, mind you, because ultimately it's always the dynamic degrees of freedom that you deal with. Okay. And this is very, very interesting, and that is that if I have n dynamic degrees of freedom, I have n natural frequencies. Okay. Now, you ask me this problem. This problem, how many frequencies does this structure have? In reality, infinite number of natural frequencies. And we will show this, Later on in this course, I am going to actually solve continuous systems, and I will show you that in reality there are infinite number of natural frequencies that any continuum structure has, any continuum structure. Okay, if it's a rigid body, if it's a system of rigid body assemblages, they don't have infinite. Okay, but any continuum structure, and remember, a framed building is a continuum. Okay, so therefore, when we take it as a 3 degrees of freedom, okay, I get only 3 natural frequencies. Which frequencies do I get? We can show that we actually get an approximation of the 3 lowest frequencies. Because note another thing that's very important, and that is that when you have omega n, you have different omega n, right? And the way you put them together is in this format. Omega 1 is less than omega 2 is less than omega 3 is less than omega n. So, in other words, they are sorted in increasing order of value. Okay. So, therefore, an infinite degree of freedom, we made it into a 3 degree of freedom. Which three natural frequencies are found? Well, if you look at this, the continuum, you will see that you get an approximation of these frequencies. Now, I said that if I use the lumped mass formulation, I only get a single degree of freedom. These two also disappear. Which one do I get? I actually get only this one. Approximation. Okay? And that is the beauty of this specific thing, and that is that all we do is we get a good estimate of the natural frequencies and the corresponding shapes of vibration, because whenever you have a specific a continuum, it has a shape of vibration, each vibration. Remember, for example, if I have this, it can vibrate this way, it can vibrate this way, so each has a shape associated with it. Okay? So, I have completed my equations of motion, and I have introduced you that ultimately the free vibration problem is nothing but an eigenvalue problem, and we also saw that since M and K are positive definite symmetric matrices, the eigenvalues are all positive and distinct. Okay? We will continue with this free vibration problem in the next lecture. Thank you very much. Bye bye.